Thank you. Thanks everybody for coming. Today we're very happy to have Serdar Yuksel visit us online. He's a professor at the Department of Mathematics and Statistics at Queen's University and will talk to us about multi-agent learning with decentralized information today. Serdar, you have an hour. Please go ahead.
Thank you, Clemens. Thank you for the organizers. The topic of the seminar series is I think, very timely, very interesting, and very long-lasting theme. And I'm happy to be able to contribute to this discussion. So this is a joint work with my former PhD student, Bora Yengoçoğlu, and my collaborator, Arslan. And the title is, hopefully, will give you what you should be expecting, and hopefully it will be informative. So multi-agent learning with under decentralized information via characterization of policy revision paths to Equilibria. It's a long title, but it's hopefully descriptive and informative. And what I'll do is I will first try to present the main ideas with some specificity, and then extend the setup to more general information structures and also policy revision processes. But as we progress along the presentation, I may have to speed up. But hopefully the ideas will be clear. Okay. So as we know, everyone who participates in this seminar series knows convergence to equilibrium is a challenging problem, and in particular for decentralized systems, even for beyond learning, even the issues on existence, and even beyond game theory in the classical what we call identical interest or team theory, having access to local information and partial information, having access to incomplete system models, being oblivious to the presence of other decision makers. These make the problems quite challenging. And this, again, without even discussing learning. And typically one tries to incorporate and utilize the structure. For example, stochastic teams. This is the case where agents have the same cost criteria and probabilistic model. Or team-like problems, for example, potential games, which are basically essentially team-like problems, where the potential function serves as the team function to be optimized. And generalizations of this type of problems, and including what I'll be referring to as weakly acyclic games. These allow for certain policy updates, which may resemble gradient-type policy changes. And then you have zero-sum games, which is another very important class of games. Zero-sum games, they resemble teams in a variety of contexts. For example, we know that in game theory, information has a very fragile contribution to the existence and perturbations of equilibria. However, just like for the team setup, for zero-sum games, more information does not hurt the agent receiving the information, and building on this insight, much information structure or informational robustness properties can be utilized to arrive at existence, near optimality, and convergence guarantees, and many others. For example, we have repeated games or symmetric games, and I'll be talking about them later in my presentation. Okay. So now to set the ideas and the context, and also following our own chronological contribution to this overall panorama, I'll be starting with a basic setup, but all of this basic setup will give the essence of the ideas on which we'll be building on. So in particular, we'll discuss a case where first we have a finite set of agents with a finite model, finite set of states, finite set of actions, and each agent has a cost function, or we can have a reward function, depending on which one you use. And imagine that each agent has a discounted cost optimality criterion with agent-specific discount parameter. And then we have a transition kernel. Now, in this case, suppose that each agent wants to minimize his own expected cost criterion. And in this case, one should be now more specific about who knows what information. So at the beginning of the presentation, I'll be focusing on a case where agents have only local action information. An agent may be oblivious to the presence of other agents. But we'll start with the case where there's a global state, and agents have access to the global state. Again, this is mainly to set the ideas, and then we'll relax this later on. And in particular, suppose that each agent as a policy maps the global state, which the agent has access to the set of local actions. And this is the strategy. And therefore, in this case, we say that a collection of policies is a Markov perfect equilibrium if for every state realization, the pointwise perturbation leads to the best response of the agent being already at the equilibrium. Okay. So again, at the beginning of the presentation, again, to set the ideas and the context, we will assume that first we will assume that a deterministic equilibrium exists. In particular, this will be the case for potential games and weakly acyclic games that we'll be considering. But then later on, I will relax this condition. And of course, as we know, for game theory, typically one has to consider randomized policies to be able to invoke the fixed point theorems. But that will come later. Now, learning. As I discussed now, in this case, the learning has to take into account the fact that each agent only has access to local action information. But for the time being, we'll assume that the agent has access to the global state. Okay. So we have access to past local decisions, past global state, and the past realizations of the costs. Okay. So each agent has no access to other agents, even their presence, and therefore we don't see their actions. But they, of course, affect us through the cost realizations. Now, if each agent pretends that the environment does not include any other agents, any other decision makers, and you may find it reasonable that each agent may run a Q-learning algorithm as if he is the only agent present. Okay? So if you just run the standard Q-learning algorithm, where is the Q function, and then alpha is a learning rate, then we know that under very mild conditions, the standard Q-learning algorithm, where the learning rate has to satisfy square summability, but not being summable, and every state action being visited infinitely often, then we know that will converge to a limit, right? But when there are multiple agents who are simultaneously updating their Q functions, then a problem arises, because in that case, as agents are updating their Q functions, they may apply arbitrary policies, because for the convergence of Q-learning, in fact, it doesn't matter how we update, how we make the selections of actions, as long as every action is visited infinitely often. But if the other agents apply a non-stationary policy, then from the perspective of any other agent, the environment will be non-stationary, and there's no guarantee that the Q-learning algorithm will converge. In fact, you can find oscillations where Q-learning with such non-stationary environments may not converge. Now, therefore, a primary obstacle, in addition to what I discussed earlier regarding decentralized information, a further obstacle for learning is that as multiple agents are learning simultaneously, the environment will be non-stationary, and therefore there may be no guarantee for convergence. Now, in a paper I mentioned about 10 years ago, 8 years ago, we studied the two-time scale algorithm. In the two-time scale algorithm, the idea is that there's an exploration period, and during the exploration period, agents apply a stationary policy. And at the end of the exploration period, they make a reflection. They say, okay, are we happy with our policy, or should we revise our policy? Okay. So at that time, this idea was novel, but there had been similar ideas in the repeated static game framework, and there are also related ideas regarding multiple time scales, where the time scales involve the relative decay to zero of the learning rates. So in particular, you can see the papers cited at the bottom, in particular starting with the paper by Borkar, but even the earlier paper also. But the idea of a multiple time scale is that as you make an update, the learning has already stabilized, and the revision is slower than the value learning, and that allows for the environment where the algorithm can be guaranteed to be converging for each exploration period. But the question is, what happens after the exploration period ends? How do we revise our policies? Now for this, I'll now define the notion of weak acyclicity. Weak acyclicity. So suppose that the other agents' policies are given, and suppose that if the other agents are given and each agent is best responding, say pi I denotes the set of best reply or best response policies. Okay, the set of policies which are best responding to the environment. Okay. So then discussed earlier, if each agent is running a Q-learning algorithm where the other agents are known to be applying a stationary policy given by the collection pi minus I, then the Q functions will converge. Therefore, the set of best replies is the same as the set of best replies where the Q functions, the limit fixed points of the Q functions are pointwise minimized. So therefore, now we define the set of strict best replies to be those which are responding to the environment. And at least for one state realization, we want this response to be a strict improvement. So the set of deterministic best replies is given by sub pi, and then a best reply is called a strict best reply if there's a strict improvement for some state x. And then we call a sequence of deterministic policies to be a best reply path such that as the paths are policies that are updated, there is only one agent who is making an update, policy update. The others are staying put. The other agents are not updating their policies. So only one agent makes the update. And the one making an update is strictly best responding to the rest. Okay. Maybe we call this a strict best reply path. And we say that a stochastic dynamic game is called weakly acyclic under strict best replies if there is a finite strict best reply path starting from each initial joint policy and terminating at an equilibrium policy. Okay. We say that a stochastic game is weakly acyclic if there is a policy revision process where in each revision only one agent, we don't specify which one, but there is one agent which updates its policy, and there's a finite length where through the finite length of policy revision processes, the policies converge to equilibrium. For example, here you can see a depiction. In this case, pi 7 is the sink, and that is the equilibrium policy. And then we assume that basically there's a policy revision process which terminates at the sink, which is an equilibrium policy. Now, weakly acyclic games is not a very narrow class of games. In particular, all stochastic team problems where agents have the same cost, same probabilistic model. We call this stochastic team or decentralized stochastic control problems with asymmetric information or multi-agent information structure. Potential games, these are basically commonly studied, especially in the recent literature. There have been many studies on potential games. And dominant solvable games are examples for weakly acyclic games. Okay. Now, here's the algorithm. The algorithm is that basically what you do is you define a sequence of step sizes and inertia parameters and a collection of exploration lengths. And what happens is each agent runs the Q-learning algorithm. But the important part is, and we will later be generalizing this, the important part is the following. The algorithm converges to a limit, and in the limit, you compute the set of best response policies, and you look at your current policy. If your current policy is already best responding, you don't make a change. But if your current policy is not best responding, then with some probability, you don't do anything. And with some other probability, you randomly select a policy among the best response set. Okay. So the reason of this adding the inertia is that this is just to facilitate that the condition. Remember, there's a condition where we required only one agent to make an update. By doing so, this guarantees that the path of the best reply path is going to be charged with positive probability under this division process. So that, for example, if this lambda weren't there, you may have had oscillations, and this lambda being there guarantees that there's a non-zero probability where only one agent makes the update. But the idea hopefully should be very clear now. The idea is that basically there's an exploration period, everyone runs a baseline policy, the algorithm converges. When the convergence happens in the limit, at the end, or not in the limit, but for large enough, at some large enough exploration length, there's a revision stage, and in the revision stage, you look at how you are doing. If you're best responding, you stay put. If you're not best responding, you select the policy in your best response set. Okay. And the theorem says the following, again, for almost 10 years ago. For every epsilon, there's a large enough t tilde such that if the exploration lengths are larger than t tilde, for large enough time horizons, the probability of being in equilibrium is at least 1 minus epsilon. So for every epsilon, there's a t tilde such that the probability of being in equilibrium for large enough k will be at least 1 minus epsilon. If you increase your exploration lengths to infinity, in fact, this is going to be the probability will go to 1. And in fact, you can also refine it to almost sure convergence. So if your sequence of exploration lengths grows to infinity, then you can select them in such a way that the policy profile will go to an equilibrium almost surely. And again, as I mentioned earlier, I try to give the main ideas here because the rest of the presentation will add a lot of structure, a lot of extensions, but the core ideas will really build on this intuition given by this relatively simple setup. So there are two main ingredients here. One main ingredient is that the convergence is uniform in the initial Q selections, as long as the Q selections start from a compact set. And also the limiting Q functions are robust to small policy perturbations. And this is important for the exploration needed for the Q-learning algorithm to converge. In particular, we define Fi to be the fixed point equation, whose fixed point equation gives me the limiting Q function. And as if you have studied the proof of the Q-learning algorithm, we know that Fi is a contraction mapping. Therefore, there's a unique fixed point. And if each agent has a baseline policy pi I when they start with, and they add a small perturbation, for example, mu j can be a uniform distribution on the actions, then we have a new policy. And the idea is that the value when you apply pi I, you make two changes. Your own cost function under pi I will change, but also you change the environment where the Q function of the other agents will also be changing by your perturbation. And both of these perturbations are small, in the sense that there's a continuous dependence on the perturbations of local policies. In particular, the lemmas are as follows. The two lemma are given as follows. For every epsilon, there's a large enough t epsilon such that uniform over all the initial selections of Q functions, the probability of the truncated Q-learning algorithm, because we have to truncate our Q-learning algorithm at some point. We cannot wait forever. Then the Q being within epsilon of the limiting fixed point, being in the epsilon neighborhood, is at least 1 minus epsilon. This uniformity is important. And also the second one is the perturbation argument. For every epsilon, there's a small rho epsilon such that if each rho i's is less than rho epsilon, then the fixed point of the baseline and the fixed point of the perturbed policy, where the baseline policy is perturbed by the experimentation, is going to be less than epsilon. So these are two important ingredients that one should be looking for an argument of this type. And then what you do is then you very carefully select the insensitivities of your best responding functions to errors. There are two errors again: the error due to perturbation and the error due to the truncation of the Q-learning algorithm, because we cannot wait forever. And then you make sure that there's a separation between the Q functions, where your best responding will be robust to small changes, meaning that your best response will not be altered. And therefore, in particular, what you show is that when the random event in which your Q, truncated Q, is within a small neighborhood of the limiting Q, then this means that your Q-learning algorithm is working as if you have fully understood, you have fully converged to the limit. And then you carefully study two events. The first event is that if I'm not in equilibrium, by the fact that I am weakly acyclic, there is a finite length L where the probability of being not in equilibrium and the probability of transitioning into an equilibrium in L time stages is going to be bounded from below. So that's very important. So in a way, equilibrium is accessible regardless of where I start from. And once I'm in equilibrium, I will stay in equilibrium because I'm best responding already. Right? So in a sense, then these two events are exactly what we need, and the important ingredient for the analysis is this EK, because EK ensures that my truncation of the Q learning algorithm is at such a long period that I am with high probability as if I'm responding to the oracle process or the idealized learning process. And then with some basic algebra, you show that your with high probability as time increases, you will be at least you'll be in equilibrium with probability at least 1 minus epsilon. Okay. And finally, with a Borel-Cantelli argument, what you show is that if your time horizon goes to infinity, by making this term summable, you show that this event is going to be summable. Therefore, this can only happen finitely many times. Therefore, pi k will be in equilibrium almost surely. But the two main ingredients basically is that the graph structure, where there is a path, where the path will take me to equilibrium, small perturbations in policies leading to small changes in the best responding function, and therefore the graph structure does not change. And also that the exploration length has a uniformity property regardless of which initial state we start our algorithm with. Now some extensions before we discuss the more general revision process. Now one can replace the best responding policy with better reply policies. Basically, you don't have to always jump to the best response. As long as you better response, you find a policy which is performing better than what you did earlier, the same ideas go through. You can enhance the class of policies, the class of games for which this holds. In fact, this will be our definition for weakly acyclic games from now on. Because we will define a stochastic game to be weakly acyclic if there exists a finite better reply path where at each iteration, one agent makes the update and that agent makes a better reply. And the post-revision process terminates in equilibrium. So we call this a weakly acyclic game. And once again, team games, potential games, they all fall into this category. One can also, for the case with team problems, one can guarantee convergence to global optimality also. But for global optimality, you have to have some memory. You have to have some experience to be embedded into your algorithm. Because if you only best respond, you lose the past, you lose the history. And without history, you may get stuck in an equilibrium, which is not a globally optimal policy for a team problem. For a game problem, you may have multiple equilibria. And for a team problem also, you may have multiple equilibria. But being globally optimal is a stronger condition than just being what we call person-by-person optimal policy, which is a Nash equilibrium notion for stochastic teams. So the point is that if you want to go beyond equilibrium, if you want to have global optimality, you will have to add some memory, but the same ideas again are applicable. Now, one criticism that we had received when we submitted our first paper in 2017 was that even though the algorithm is an independent learning algorithm, there is a condition of synchronization. Is that each agent has to update their policies at the same exploration periods. And for some applications, this is realistic, where there's a common clock and there's a common decision-making period to be made. But for many applications, that's not. And the answer to that question is that if you allow the agents to have persistent learning, where the learning rates do not go to zero, then the same ideas go through in that case also. So because you do not have to have the same exploration lengths for each agent, as long as the agents are persistently learning, because the learning rate is a constant. Of course, in this case, you have a Markov chain. The Markov chain will have an invariant distribution asymptotically and with high probability that invariant measure will have the mass on an equilibrium policy at a very large probability. And finally, you can apply the same ideas to continuous spaces. Because for continuous spaces, you can show that small perturbations in your dynamics for weakly continuous Borel measure valued MDPs and teams, they can be approximated with finite models, and you can imitate the finite ideas here to that case also. Okay. Now, the above, in a sense, presented some of the main issues: non-stationarity, local information, and a technique. And the technique was to introduce a graph theoretic formulation for the post-revision processes. And then we've been able to arrive at guaranteed performance bounds, ensuring that we converge to equilibrium. However, we can do more, and we can do more. In particular, we can do more by extending the class of games to be considered, but also extending the informational access of each agent. So far we discussed the case where each agent has only local action information, but we require that there's a global information available, global state information. But ideally, we want to relax not only the local action information, but also we want to be able to relax the notion of local state information also. Okay. Then what is the big question now? The big question is now, you run your algorithm. If you are best responding, you stay put. You don't change your policy. But if you are not happy, then you make an update. Then the question is, okay, how do I make the update? How do I shift to a new policy? So far we discussed the case where you best respond or you better respond. But these types of policies have a general terminology. These are known as the win, stay, lose, shift algorithms. Basically, if you are happy, if you're winning, you stay with what you do. But if you lose, then you shift. You shift your policy. Okay. So is there any questions so far? So hopefully the idea so far hopefully should be clear. But now now we'll try to expand the scope by a little bit. And for this now I'm again going to be embedding the discussion earlier into this formulation to come. In a way, we are going to be weaving our policies to be our in a way actions in the normal form game formulation. And suppose that we have n agents, we have a set of actions, and we have a set of rewards or costs. And each agent, again, selects an action. But again, please keep in mind, I'm viewing this as a normal form game formulation where the policy in the previous part of our presentation can be viewed as an action. And so each agent receives a reward based on the profile of actions of each agent. And then each player's reward depends on the joint action. And again, for the time being, I'm going to be assuming that policies are still deterministic. They're not randomized for now. And then I discussed this earlier. We have the idea of better response, right? Better response is given the rest. A policy is better response if given the rest of the agents. If I move to a new policy, the new policy will perform at least as good as the existing policy. Okay. So the basic action is the best. This is a better response, and best response requires that not only I'm improving, but I'm improving to the best possible reward. Now, and then we say that if a given action is not best responding, then the agent is not satisfied. That's going to be an important terminology, which we will be building on very soon. And an action profile is basically a Nash equilibrium if each agent is already best responding to the rest of the agents. Okay. And once again, pure Nash equilibrium may not exist, as we very well know. Okay. Now, with that earlier discussion in mind, and with this presentation, with the slide which I just presented, we can now define a best response graph, a better response graph, and a satisficing graph. Okay. Now, the best response graph is what I've already discussed earlier. Each agent, you are updating your policy profile, and you are best responding, or you are better responding, or what I'll just introduce next, the idea of the satisficing graph. So the best response graph is a directed graph where if an agent, basically what you do is you have a sequence of policy profiles. In a sense, I'm in A1 and I go to A2, which means that there's an edge between the policy profile A1 and policy profile A2. Only if, and if and only if A1 is already best responding to the other agents, then A2i is the same as A1i. I'm not changing my policy. If I'm best responding, I stay put. But if I'm not best responding, then agent 2i will move into a best responding policy. Okay. This is what we have already discussed in the previous part of the presentation. And you can do the same thing so let's give an example, the discoordination game. In this case, as you see, if I'm starting 1, 0, then the upper agent will go to 0, 1. If the upper agent goes to 0, 1, then the lower agent will go to 1, 0. And then if I'm here, then the upper agent, this agent is happy, satisfied, but the upper agent is not. He's going to best respond to 0, 1, and then you have the cyclical graph. And the better response, again, is just a relaxation. In this case, once again, if you are best responding, you stay put. If you're not best responding, you are going to be moving into a better responding policy. Okay? So therefore, by definition, this graph is more relaxed than the previous graph, because in that case, I required to be the best response. Here, I just wanted to be a better response. So definitely, the best response is a subset of a better response. Therefore, the graph is going to be non-decreasing in terms of the set of edges. And as we recall the definition of weak acyclicity, gains.
Serdar,
Yes, Clarence.
just quick clarification. In these definitions, it looks like all agents could switch to a best response profile, or is it still that you're thinking of it as one agent only is switching?
That's right. So in this case, in this case, you see, in this case, you can, when they implement it, Clemens, when you implement it, you take it into account. But you are correct. In this case, we allow for simultaneous changes in this definition. But when you implement it by adding the inertia, that will take care of it. But you are correct, Clemens. That's a very, very, very good point.
So, but these are different kinds of games, no? Where, I mean, this is much stronger if I get these paths to limit to equilibrium, then, or are these kind of closely related?
No, Clemens, you are absolutely correct. So in this case,
okay.
The restriction that only one agent makes the update is not embedded in this definition yet.
Mm-hmm.
But when you implement it, you add an inertia, and that inertia brings it back to what I discussed earlier. But you are absolutely correct.
Oh, okay. Got it. Yeah.
But when you implement it, the response in such a way, let me just show this to you. So show the algorithm. You see, with some probability lambda, you stay put. With probability 1 minus lambda, you switch. So you see, in a way, the graph is still this graph, but then there's a probability that you preserve your policy. And then with probability, lambda I to the power n minus 1 times 1 minus this expression, right? Then you will have only one agent updating policy. But
okay, yeah, no, I was just thinking of games where I guess the path where everybody switches leads to Equilibria versus games where the path where a single player is switching. But
so this is the importance of inertia.
Okay.
Right. So let me just discuss this. Right. We define the weak acyclic games. And as we discussed earlier, for such games, then independent learning is guaranteed, as we saw earlier. And Clemens made a very good point, and this should be maybe highlighted in this discussion. Okay. Now, existence of pure Nash equilibria does not suffice for being weakly acyclic. For example, is an example where, in this case, you can see 5, 5 is our Nash equilibrium, right? But if I'm at this policy profile, then the upper agent is going to be better responding or best responding. Then you go to 1, 2, and the left agent, the up right agent, she'll be going from this profile to this profile, and then you have this cycle, and this cycle will never go beyond these two submatrix entries. So to be able to go to 5, 5, I need to somehow go to the upper row or the lower column, but that I cannot go because my best response paths will not push me up or push me to the left. And now the new definition, satisficing graphs. So the satisficing graph is a directed graph where if I'm best responding, I stay put. And if I'm not best responding, I can do anything I want. Okay. So in a sense, this second item is redundant because it doesn't constrain me at all. But the first part says that if I'm best responding, I stay put. That's the only condition. So therefore, by definition, you can see that the best responding is a subset of better responding, is a subset of satisficing. You see again, in the satisficing part, the key ingredient is that if I'm not happy, I can do whatever I want. Okay. So you see there's a difference. There's no policy gradient type. There's no, it's just a pure exploration. So then we define a game to be generalized weakly acyclic if it admits at least one Nash equilibrium, so far in this case pure. And for any initial positive profile, there exists a satisficing path from the initial profile to a Nash equilibrium. So this is the definition for, remember, we defined weakly acyclic games earlier. Now I'm defining a generalized weakly acyclic. In this case, I replace the best response or better response paths with a satisficing path. And lemma, if a game is weakly acyclic, then it's also generalized weakly acyclic. This is by definition, because we strictly expanded the set of edges. There are games which are generalized weakly acyclic, but not weakly acyclic. And not all games with pure Nash equilibrium are generalized weakly acyclic. So let's repeat the second and third items. There are games which are generalized weakly acyclic, but not weakly acyclic. And not all games with a pure Nash equilibrium are generalized weakly acyclic. Let's give examples for this. So let's look at this first example. As we discussed earlier, this is an example where, as we discussed earlier, this is not weakly acyclic, because if I'm in 2-1, for example, then the upper agent will best respond to 1-2. Then this agent here will go to 2-1. Then the column agent will go to 1-2, 2-1, 1-2, right? It'll be a cyclical path, and they will never go to 5-5, right? On the other hand, if I'm in 2-1, and if the column agent is unhappy, he can go wherever he wants. He can go to either 1-2 or 0-0. In particular, if he goes to 0-0, then we can find 5-5, right? So this is an example where I'm generalized weakly acyclic, but I'm not weakly acyclic. And the second one says that you may have a game where there's a pure Nash equilibrium, but you are not generalized weakly acyclic. So for example, in this case, what you see is the following. Suppose I'm in 1-0. If I'm responding, for example, the column agent is not happy, right? He can do whatever he wants. But if he goes to any of these, to 0-1 or 1-0, right? So what you see is that the only time I can hit a column, the top row or left column, it'll be either 0-1, 0-1 here, in which case the column agent is happy. There is no incentive for the column agent to go to 1-1. Or the only case where the row agent hits the left column is at 1-0 or 1-0, right? Because I'm starting here. I have to go either this way or this way, right? But if I'm hit at 1-0, there is no incentive for this agent to go to 1-1 because he's happy, right? So this is the problem. You see, when you're satisficing, there's no incentive for you to explore. But in a sense, these two examples, they give us the hint on what to look for, what the conditions we should be having to be able to arrive at equilibrium. Is there a question on these examples? So then we can define a satisficing Markov chain. A satisficing Markov chain is a Markov chain where if I'm best responding, I stay put. If I'm not best responding, randomly select any policy profile. Therefore, by the construction we made earlier, we can easily state the following. A game is a generalized weakly acyclic game if the satisficing Markov chain constructed earlier, where again you stay put if you're happy, you randomize explore, you randomly select any other policy if you're not satisficing, then the Markov chain is going to converge to a Nash equilibrium almost surely. Right? And the idea is exactly what I presented earlier. Right. Now, then an important question. Now we've now seen that the relaxation is consequential. There are games where the relaxation is very, very critical. Now let us define. Now the idea is to try to find conditions for which a game is generalized weakly acyclic. So let's have a definition. So a policy is a strict best response if given the other agent policies, the selection is strictly better than every other possible action. Because you are strictly best responding if there's a separation between the action and all the other actions, given the rest of the environment. Okay. And a Nash equilibrium is strict if I star is a strict best response to A minus I star, and this being so for every agent. A theorem, if a game has two players, and if a strict pure Nash equilibrium exists, then this game is generalized weakly acyclic. So because every two-player game which admits strict pure Nash equilibrium is generalized weakly acyclic. This is an almost immediate result, but it sets the stage for the case where the number of agents is larger than 2. So the idea is the following. If both players are satisfied, we are in equilibrium. There's nothing to prove. If we are both unsatisfied, we can both switch our policies, and then we go to an equilibrium. And if one player is happy and the other is not happy, then the one who is not happy can go to the corresponding component of this equilibrium for that agent's coordinate. And if the other agent is happy, everything's fine. If the other agent is not happy, the other agent will go to the coordinate corresponding to the policy corresponding to his coordinate. And if the agent who just switched earlier, if he's happy, he stays put. If he's not happy, he comes back to where he was, and therefore we arrive at equilibrium. So it's a very simple idea, but what you can do is you can apply the same idea to the n-player game, where if you have an n-player game, and if there is a strict pure Nash equilibrium, it doesn't have to be unique, but you want one strict pure Nash equilibrium. And if for each subgame induced by this pure Nash equilibrium, the subgames have a uniqueness property, then the game is generalized weakly acyclic. So in particular, you can just imitate the same idea in a sequential manner to arrive at the equilibrium. So this is a characterization, and in fact, you can show that there are examples also for Markov games where the same construction applies. So the point is that we can find conditions for a game to be generalized weakly acyclic. And in particular, as the examples I gave earlier hint towards, strictness is important because strictness is what forces the satisficing to discourage being complacent.
You have a question.
Yes, please.
Yes, so I just wanted to make sure what you call a sub-game. You mean a game, it's not like an extensive form game. So you mean something where you restrict agents to just a subset of the strategies? What do you mean by sub-game?
What I mean is that suppose there are 3 agents. Suppose one of the agents is stay put at a given equilibrium, and the others are playing the game.
Okay.
So now, so far we discussed the case where we focus on pure strategies, right? But the main issue is that, as we know, pure strategies is very restrictive. We have to go beyond pure strategies. Now, so far we made observation for weakly acyclic games, for generalized weakly acyclic games. But we want to be able to have a theory for randomized policies, which allows for randomized policies. Now, when randomization is allowed, you can show that, in fact, satisficing paths to Equilibria always exist. So it's basically you just need very, very mild conditions. You just need a very minor mild continuity condition. It's a perturbation argument. And this also applies to Markov games. All you need is that your cost function has to be continuous in your action or in your policy in this case. So again, the proof is just a perturbation-based argument. However, the problem is that in a way, the proof of this argument is why it cannot be consequential, because it requires us to have an uncountably many policies, uncountably many paths to be able to reach equilibrium. And when you do implementation in a learning algorithm, you have to restrict yourself to at most countably many and really finite many policies. So therefore, we need to go beyond just satisficing, and we need to go to what you call epsilon satisficing. Again, this just has obvious meaning. It just means that if you are epsilon happy, you stay put. If you are not epsilon happy, then you revise your policy. Okay? And now, but this is a much harder problem. Because when is it the case that you have a game where there's an epsilon satisficing path? Okay? Now, in a paper in 2023, we introduced this notion of epsilon satisficing, and then we showed that all symmetric games and also 2-player games, they satisfy this property. And in particular for symmetric games, because we are also able to show that when each agent approximates the set of policies by quantizing their set of stationary randomized policies into a finite collection of policies, the finite collection of policies also satisfies the satisficing property, and thereby we are able to arrive at a learning theorem, which is not applicable for arbitrary 2-player games. Okay. And now this will motivate what I'll just be presenting. But the main idea is that for pure strategies, satisficing and weakly acyclicity, they work really well. We can obtain precise characterizations. We have a learning theorem. But when you go to the continuous setup, in particular when you have mixed strategies, then yes, satisficing paths exist under very mild continuity conditions. But for them to be consequential, I need to be able to restrict myself to epsilon satisficing paths. But the question on when epsilon satisficing paths exist is much more difficult, much more challenging. But the special case where that holds is the case with symmetric games, and also the case with two-player games. Okay. Now let's discuss the symmetric game case. I know I don't have about 15 minutes now. So a stochastic game is symmetric if basically when you perturb the agents, the values are also when you permute the identities, the values, the transition kernel stays the same because it permutation invariant, but also the cost functions are also symmetric in the sense that if I like something to be done to me, Clemens also likes to be same thing be done to him, right? We are not minimizing the same cost functions, but we have the same rewards and same costs when the environment is at a given stage relative to our perception, our actions. Okay. Theorem: if I have a symmetric stochastic game, and if there is an epsilon equilibrium, then this game has an epsilon satisficing property. Okay. So I think it's a very practical result. It says that if I have a symmetric game and all I want is that there is an equilibrium, epsilon equilibrium, then there is a satisficing path. And now the proof argument is, I think, very simple, very interesting though. The idea is the following. So if you have n agents, what you want is, you want the agents to be in such a way that in the end of the policy revision process, we want them to converge to equilibrium. And here's the idea. The idea is that suppose that there are k agents where each k agent have the same policy and the rest have different policies. And we'll inductively construct this set of agents and we'll increase it to n-1. And in the final stage, they will arrive at equilibrium. So now, because the agents have the same policy, then either they're all happy or they're all unhappy. So this is the important part. Because of symmetry, the agents who are in the same policy profile, so basically all players in CK have used the same policy, because they have the same policy, from their perspective, the rest of the environment is the same in a way. So therefore, either they are both happy or they are both unhappy. Now, if all the agents in CK are unhappy, then they will imitate an agent which is not in the set, and the size will grow by 1. Or if they are all happy, someone outside is not happy, and that person is going to imitate them. You see, it's a very simple argument, but it builds on the same intuition that we discussed earlier for the pure strategy setup. And this guarantees that the size will increase up to n-1. In n-1, then either they are all happy or they are all unhappy. And if they're all happy, they will go to an equilibrium, which is going to be whose existence has been guaranteed. So note that the final equilibrium does not have to be symmetric. All we want is that there is an epsilon equilibrium. Right? Now, the same similar idea can also is applicable for the two-player game setup. But for two-player game setup, the problem is that for learning, we have to do approximations, and approximations, unfortunately, they do not preserve the paths. Right? Unlike the symmetric games. In a way, symmetry is preserved by identical quantization of policies. Okay, now again, reflection. So then what we show is the following. When is it that Winstead shift algorithms result in equilibrium? For what choice of update rules and for what classes of games? So far, we discussed the weak acyclic games and general weak acyclic games for under pure strategies. And then we discussed the case where for symmetric games, under the existence of an equilibrium policy, we do have indeed a satisficing path to equilibrium. So then in the next now few minutes, I will give an example involving mean-field games, because mean-field games is a very important class of symmetric games. And in a way, this will be an application of the ideas. So many of you have seen what a mean-field game is, also in the seminar series. You have local actions, local state, but then the mean field is through which the dynamics impact each agent, as well as the cost incurred for each agent's realized costs. Local state, local action, mean field, local state, local action, and mean field, they impact the cost and the transition. Okay. Now, the important question in this case, when we apply, and also one, I think, manifestation of the power of symmetry is that the information does not have to be as rigid. For example, you can have global state information, you can have mean field information, but also you can have only local information or some partial mean field information. Okay. So for each of these, you can have a corresponding learning theorem. And I'll be discussing this very briefly. But to set the ideas, because time is short, let me just quickly go through. I'll just skip this part. Reflection. Again, these are mainly to introduce ideas from mean field theory, which I will skip. Right. Now, if the number of agents were infinite, we know that there's this notion of mean field equilibria. In the mean field equilibria, as you know, there are two conditions. Optimality condition, each agent optimally responds to the mean field. And the mean field has to be consistent with each policies, meaning that the mean field is generated by the policies, right? So, and you can find conditions for the existence of mean field equilibria. Now, let us first study the case where each agent knows the entire global state. There are finitely many agents, and each agent sees his own local action, but also sees the entire collection of states for each collection of agents. In this case, you can show that by the same ideas as we discussed earlier, there is an Markov perfect equilibrium. In fact, this is going to be an exact equilibrium because, once again, as I mentioned, in this case, I first assume that I know everything in the system, except I only see my own action. I don't see the actions of other agents. In a way, this is a special case of what we discussed earlier. How about the case where I only see the mean field state and I only see my own local action? In this case, you can show that there exists an equilibrium, and the equilibrium is going to be symmetric. So there's a symmetric equilibrium. So even though I only see my local state and the mean field term, you can show that there exists an equilibrium, which is going to be like a Markov equilibrium in this case. And for the case where I only have local state information, because I don't see the mean field, what we can show is that as the number of agents goes to infinity, then there's an epsilon equilibrium when every agent imitates the mean field equilibrium policy applied by each agent independently. Okay. So in a sense, we have an existence condition. It's exact for global state and mean field state, but it's epsilon exact for the case with local agent information when the number of agents grows to infinity is large. But for the global state information available, or the case where each agent only has local state and the mean field, the existence is universal for every number of agents, for every n. Okay. So now each agent is now going to apply what we discussed earlier, the satisficing paradigm algorithm. So each agent then is going to apply their best response. Let me just give you the algorithm. And here's the idea. The idea is that if each other agent applies a stationary policy, then agent I will run a Q-learning algorithm as if what they see is their state, and they naively look at their best response sets based on what the others are doing. Okay? So in a way, I'm running Q-learning algorithm as if what I see is my true state, as if, again, I'm the only agent, and what I see is my true state. I'm running a Q-learning algorithm. And the question is, what do I do with this algorithm? So again, I'm running Q-learning algorithm as if what I see is the true state. Again, there are three cases. The first case is yi is the global state. The second case is yi is the mean field state and my local state. And the third case is yi is only my local state. So the Q-learning algorithm, I'm running it. I'm also running what I call the value learning. In this case, this will tell me how well I'm doing. And then at the end, what you do is the following. So the first thing I should say is that this algorithm will converge. So even though the Q-learning algorithm involves a non-Markovian environment, because you see, when I only see local state, and when I run my Q-learning algorithm, there is no guarantee that my Q-learning algorithm will converge, because the standard Q-learning algorithm requires that I have a finite state Markov chain. And the error in Q-learning is what we call a martingale error. And that is not the case in the setup we are discussing here, because we are discussing a non-Markovian environment. But nonetheless, the proof method can be adjusted to trade off the martingale noise with the ergodic noise. So the point is that the algorithm will converge. And then what you do is now, your value will converge, your Q function will converge, and each agent will face a revision question. How well am I doing? So then each agent will do the following. You look at the converged Q function and converged value function. If you're happy, you stay put. If you're not happy, you change your policy. And we call this a subjective equilibrium because what your algorithm tells you is not the exact best response. Yes, the algorithm will go to a fixed point, and you're responding based on the algorithm. And then, in a sense, we call this a subjective epsilon algorithm. And let me just say the following. This will be the slide before the last slide. Let me just show you, and then let me just show you this theorem, and that's the end of my presentation. So suppose that each agent follows the satisficing algorithm framework. Each agent runs their Q-learning algorithm, imitating that their state is the actual state. I'm running the Q-learning algorithm as if what I see is my state. The algorithm will converge to a limit, and I will revise my policy based on how well I've done at the end of the exploration period. As long as there exists a subjective equilibrium, and we know this exists in three cases, with the global state, with the mean field state, and also with local state when the number of agents is large. Then the algorithm will converge to an equilibrium, but a subjective equilibrium, right? So this is the important part. The algorithm will converge to a subjective equilibrium. And again, the proof is that for large enough exploration periods, my Q function will converge to something, my value function will converge to something, and I'm responding. If I'm happy, I stay put. If I'm not happy, I explore. And then because of symmetry, satisficing paths exist. This is where the ideas come together, and therefore you converge to an equilibrium. So in conclusion, we studied multi-agent learning under various information structures. We first discussed the case with pure strategies, weakly acyclic games, by a paper from 2017. Then we extended ideas to generalized weakly acyclic games by replacing best responding with satisficing. And then we extended ideas to randomized policies. And for this, we noted the need for epsilon satisficing. And in particular, we made the point that when you do epsilon satisficing, if you only have access to partial information, convergence can only be to a subjective equilibrium and not an objective equilibrium. And then we applied the ideas to n-player mean field games. We proposed the idea of subjective Q-learning equilibrium, and then we established existence and convergence. So thank you for your patience. I'm happy to answer questions you may have.
Thank you very much, Serdar. Very, very interesting talk. Lots of papers to discuss. Yeah, let's open it up for questions. Please go ahead. Anybody who wants to ask.
Well, I don't, it's not necessarily a question. It's just wondering, there was a work presented in this, one of the first sessions of this seminar by Basil Tarbush about random graphs, and something that sounds a little bit like the acyclic thing that you're mentioning. Maybe it fits within, maybe your algorithm extends to the set of games that they identify. There.
Sure, I'm not aware of it. Could you, maybe we can follow up and exchange references?
I'm happy to send you the references, because maybe it means that you can apply your algorithm to things that they identify, a large class of games.
Go ahead. Yeah.
Hello. Thank you so much for the talk. It was very interesting. I'm working on something very, very similar. But okay, first the question. My question is, first of all, about the better response graph, best response graph, and satisficing graph, just to make sure I understand it. So best response and better response. So I have, for each policy profile, I have edges only when one agent can better respond or best respond. Better respond or best respond. Then I have an edge, exactly then. And now in satisficing graph, I have the best response edges, but then also I have some arbitrary additional edges. Is this correct?
That's right. That's right.
Okay, I understand. Okay, good.
Okay,
now, yeah, that's it actually. I just wanted to make sure. Good. And now question 2 is, yeah.
So the only restriction is when you're happy, you're not doing anything else. You're just staying put.
And then if I'm not happy, I can do whatever I want to that I think will improve my situation, basically.
No, whatever you want. You can improve, you may not improve, whatever you want for the satisficing case. But for the best response or better response case, yes, you have to improve.
Okay. Now, second question is, so you have normal form games. So obviously, is there some kind of extension to extensive form? And also, especially this weakly acyclic definition, I think you probably need to extend that. And also the satisficing graph, the whole idea of that. Is it extendable to extensive games?
That's right. That's right. Yes, yes, you can do that. Yes, right.
Okay. Okay, good. Thanks.
One open question, as I mentioned, is basically when you go to epsilon satisficing, so in a sense, it's much more difficult, it's much harder to. So symmetry is one very useful special case, and also the case where if you have deterministic policies, in a way, epsilon satisficing is the same as zero satisficing because the paths are robust to small changes. However, when you go to games which are not symmetric, so basically it's an open area.
Okay.
Yes, Artem, please go ahead.
So here we're showing that this converges in the limit, right? Eventually. Is there sort of interest or any steps forward for like the computation complexity of this? How many steps are we taking? Can we put it in, some of the standard complexity classes for TFNP and things like that? Or not much thought on this yet?
No, Artem, I think this is I think a very natural next step because here the complexity is in two ways. When you do the epsilon satisficing, in a way, it's a continuity argument. You are approximating this class of pure strategies with basically finitely many pure strategies. So there's a trade-off between epsilon and the number of strategies that you have. And the induced Markov chain will have a much larger cardinality. And of course, when you do your Q-learning, of course, you see Q-learning itself is very challenging here because you say in this case, when you do the subjective Q-learning, the main issue is that this is not the standard Q-learning. In standard Q-learning, no matter what you apply during Q-learning, your limit will be the same Q function. But in this case, because your system is non-Markovian, your policy itself affects your limit. So therefore, the analysis is significantly different from the analysis of the standard Q-learning algorithm. And we know that standard Q-learning algorithm is already a very, very slow algorithm. So but there's definitely much to be done. I mean, here, in a way, we try to give a more like structural properties that one can look for. And I think there is hopefully a lot of room to expand, improve, and generalize regarding both algorithmic side and also the complexity side.
Okay, thank you.
Any more questions? Maybe I can add to this. So the mixed strategy quantization argument, I guess there you also run into a big complexity issue, right? Because especially even if I'm only looking at stage games, and I have a couple of actions, and I want to really represent as many mixed strategies as I can, going to run into problems pretty soon. But then if it's even a stochastic game, it's going to be even more difficult to represent this in a Q matrix and learn.
That's right, Clemens. Yeah, I mean, then you'll have to, in a way, quantize probability measures. And but nonetheless, I mean, at least in principle, even when your state space is a general Borel space, you can show that the invariant measure is continuous in finite perturbations, finite model approximations. Like you partition the domain, you partition the range. But again, when it comes to implementation, that's right. It is very time consuming, but it's possible. Like, for example, our students they've implemented these algorithms.
Could you actually explain a bit more why symmetry is necessary for the mixed strategy search? I didn't really follow there. It seems like, you know, if everybody is unhappy, they could be unhappy also in the asymmetric case.
Right. You see, maybe kind of, once you see the proof sketch, you will see why it's so critical. So you see in the proof sketch, the idea is that start with each agent doing something different. So there's at least one agent which is unhappy by definition, right? So that agent can randomly pick another agent and can imitate the other agent. So then you have two agents which are doing the same thing. They are either happy, they're either happy or simultaneously, or they're unhappy simultaneously, right? And then the idea is that, okay, these agents, if they are either happy, they stay put, and someone else will imitate them, join the club, or they're both unhappy, and then the two of them simultaneously will imitate another agent from the happy club, or even the unhappy club, right? So anyway, for the argument, it's very important that symmetry is there, because symmetry is what tells me that agents who are applying the same thing, they will follow the same update profile. They are always either going to be happy or unhappy. When you break this, there's no guarantee that when I am happy, right, the other agents may make an update, and the happy one can become unhappy, and vice versa. So in a sense, you lose the structure that this algorithm gives you. And it's very difficult to establish a profile where you will eventually arrive at an equilibrium. I mean, this is for the epsilon satisficing discussion. For the case where you have pure strategies, it's a continuity argument. There, in fact, there you can show that if the values are continuous, then you always have a satisficing path. But when you have the epsilon satisficing, it's a very discrete algorithm, very discrete object, and it's very difficult to pin down.
And I guess the root cause is that you need indifference at the equilibrium, right?
That's right.
It's kind of back to the existence of pure strategy. Nash is not enough for generalized cyclicity. Okay, thanks.
There's a question by Yannick. Please go ahead, Yannick.
No, just to precision on what you just said. So you explained that if the game is not symmetric, so the argument does not work. But then do you have counterexamples when the game is not symmetric? Or is it just that you don't know how to make the proof, or do you know that it's not true?
We don't have a counterexample, but it shouldn't be too difficult to construct counterexamples. But no, we don't have a counterexample yet, Yannick.
Okay, but you believe it's not true.
Yes. I mean, I think epsilon satisficing is that's right. That's right. I mean, if it were true, it would be a very rich result. But I think it would be fantastic if this can be studied.
Okay, thank you.
Because you see, the difficulty is that all we have is that if I'm happy, I stay put. If I'm unhappy, I can do anything I want. But the epsilon satisficing path, in a way, restricts me. If I'm epsilon happy, I stay put. And this restricts what any given agent can do. And it is very difficult to study. When epsilon is 0, you can just resort to continuity and the perturbation, because there are infinitely many paths. Then you can show that there is some path where I will eventually break being not in equilibrium, but that doesn't apply for epsilon satisficing. But based on your question, yes, we probably haven't spent enough time to obtain a negative result.
Okay, thank you.
Any more questions? Okay. Well, again, Serdar, thank you very much for the very informative discussion.